Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we were discussing about various case studies of shape memory alloys. The case studies means that different alloy system that exhibit the shape memory effect and pseudo elasticity. So far we have discussed about ferrous alloys and non-ferrous system. In non-ferrous system, two important system has been discussed. One is copper zinc and other one is copper aluminum. So, in copper zinc system we purposely add some amount of other alloying element, so that we can tune the transformation temperature. Very similarly, in case of copper aluminum system, we purposely add nickel and some amount of beryllium, so that we can tune and simply tune the transformation temperature, means MS temperature. Among all the very important non-ferrous system, titanium nickel plays a very major role and on the shape memory alloy its application, because it has a very wide range of application and we will go into detail of it. So, let us start today's discussion with the nickel titanium system. Before going to different phase transformation in nickel titanium, we must try to look at its phase diagram first. So, in the left hand side you see here the titanium and nickel in the two extremities of the phase diagram and versus temperature. So, titanium has a melting temperature of quite high, above 1600, nickel also have something like 1460 degrees centigrade or above, and so in between the around 50-50 the important phase, that is nickel titanium phase, which exhibit the shape memory effect, and this nickel titanium phase has a B2 crystal structure. Now, you can have a look that there are many other competing phase along with that nickel titanium phase, which has a rather very limited solubility if you decrease the temperature, and here almost very less, and if you go below 600 degrees centigrade, there is also again a eutectoid decomposition, very similar like copper aluminum system, and so we must have to overcome such a situation. So, the competing phases here are titanium 3 nickel 4 and titanium 2 nickel. This is like a enlarged or a larger version of this domain. This region I have enlarged here, and the temperature here is shown in Kelvin. So, you can have a look that even though around 1400 K there is a large limit, but ultimately it completely reduces, and these are all experimentally measured solubility limit curve with nickel content. So, one has to design the alloy very carefully, so that we get the composition and temperature and transformation temperature accurately. So, mostly people prefer that this nitinol, which has been discovered quite a long time ago, it has a composition range, very limited range. People exploit the properties like 44.5 to 45 percentage of titanium, and let us say the 50% of the rest of the component. Sorry, here it should be the nickel. So, let us once again have a look to the diagram here. So, your nickel is a little bit here is the less one, and now the phase transformation occurred that has a ordered nickel titanium phase that has a BCC A2 structure. We are talking about the nickel titanium system at higher temperature, which is shown here and marked here as 1. So, this has a BCC structure, which is a A2 structure, and if we cool it down, so around 650 to 700 degree centigrade, there is a diffusional transformation. Means if we cool it down, so 700 means something around 923 degree centigrade. Around this temperature range, the B2 that phase will appear, which is a ordered phase, which is known as nickel titanium. Here I marked here as 2, and this B2 phase is responsible, that is the parent phase, which transform martensitically to a B19 type of martensite structure, and these here it is shown here as nickel titanium 3. So, the shape memory effect that is achieved in this composition range is lying in this particular reversible transformation, because here there is a cesium chloride type of structure, which is the parent austenite structure that transform martensitically to a B19 structure, and once again if you reheat the B19 structure, it will again be transformed into B2 type of ordered structure. However, once again I should remind you that there is a competing other transformation that occur which are not at all desirable in this particular case. Now, in case of this nickel titanium, where nickel titanium 2 means the ordered structure that produces at a relatively lower temperature than 700 degree centigrade, that particular phase will be decomposed into titanium 2 nickel and titanium nickel 3, and this is a eutectoid transformation which is not desired at all. There are some other transformation like titanium 3 nickel 4, which again further decomposes into titanium 2 3 or titanium nickel 3 type of phase. So, there are so many different transformation occur, and this could be somehow avoided by adding some amount of cobalt into the system, which retard those transformation and stabilizes the nickel titanium. However, once again there are so many different complex transformation that occur in titanium nickel system, because I said about the B2 structure that transform into B19 type of martensite structure. So, this is the martensite structure. However, in some cases there are B19 dash phase forms. So, here this dash stands for a ordered type of martensite, and this martensite has a monoclinic structure with a symmetry of P21 M. Okay. So, this is a M stands for actually monoclinic. So, this is a monoclinic structure, and you could easily realize how difficult these transformations are, because once the austenite is ordered and martensite is also ordered, during reverse transformation all these ordered structure should come back, otherwise thermodynamically it is not at all favorable. And therefore, we have to look at how these transformation sequence are linked with there. So, let us have a look how this B19 or B19 dash phase forms, and whether there is some other phases again formed or not. The austenite phase, where the B19 dash is a common transformation, in some cases it has been observed that before B19 martensite formation, there are competing phase, there is a R phase that form. Here R basically stands for a rhombohedral type of structure, means before a B19 martensite, the B2 during cooling transform into R, and then this R will transform into B19. And such a particular transformation occur when 2 to 3 atom percent of nickel is replaced by some iron and aluminum. So, there is such a problem appear. However, there are some benefit of R phase formation. So, this intermediate phase or R phase that appear during cooling of this B2 structure is a pre-martensitic phase. We often call it as a pre-martensitic phase, and due to such transformation we get a very small shape memory effect, because ultimately we need to deform B19 plastically, and then during heating it should go back to B2 phase, and that is that amount become less, and therefore, we get very less amount of shape memory effect. Now, it has been observed that if R phase that appear before B19, means if such a sequence of transformation occur, then the transformation occur from B2 to R to B19. Otherwise, if B19 appear first, means during any transformation, if B19 has formed, then we can simply rule out the formation of the R phase, because R phase will never appear in the structure or in the microstructure. So, we can we can think about why we really need this R phase, because this R phase formation produces very small amount of strain, transformational strain, and that is why sometimes it may or may not be preferred. However, we can control this R phase formation, because when the alloy contain iron and aluminum, these R phase transformation become more favored, or sometimes during aging itself, if some titanium 3 nickel phase type of precipitate appeared in the microstructure, then again this R phase transformation will be promoted. Or sometimes after cold deformation, to reduce the vacancies, we reheat the microstructure all the or the sum of the component, and during that time also some times the R phase formation is more promoted, and this is a very general sequence that the transformation will occur, that directly from a B2 type of austenite, instead of forming directly B19, the transformation goes in this way, that first R phase forms and then it goes into B19 type of martensite. However, such a transformation is all are linked with nickel titanium system only by little addition of iron or aluminum. However, people have tried with copper to replace this nickel. So, here you see I write here, like if this is the total 100%, we add copper purposely in order to replace nickel. However, copper addition never goes beyond 25 atomic percentage. So, means like titanium 50, nickel 25, copper 25, that is the maximum composition, and people do not prefer more than that, because there will be no other transformation will occur and martensitic transformation will be retarded. So, in a very low copper content, in case let us say in the range of 7.5 atomic percent of copper, this B2 will transform directly to B19 dash. Here this is a ordered martensite structure. However, in the range of 7.5 to 15, it has been observed that B2 first transform to B19 and then B19 will undergo a ordering, that is B19 dash. Whereas, in case of a higher copper content, we may get a direct B2 to B19 type of structure. So, you can see the sequence of phase transformation in a nickel titanium system is very complex, and there are many different competitive transformation like eutectoid transformation, which I discussed just a few minutes ago, that the eutectoid transformation, like here the titanium 2 nickel type of phase, titanium 2 nickel type of phase, or titanium nickel 3 type of phase, or let us say the titanium 2 and 3 type of phase, or 3-4 phase. These are competitive phases that evolve with the nickel titanium phases. However, even though we prefer a higher amount of nickel content in this composition, but mostly there are in the martensite itself there are many different variants that appear, like instead of B19 we may get sometimes B19 dash, or sometimes we get R phase and so on. So, there are 3 phase we have learned in a nickel titanium system, and now we will try to move a little bit further and to learn how the path is chosen for such a B19 from B2 parent phase. Here a schematic diagram is shown to understand the crystallography in nickel titanium. So, the larger field bubbles represent a particular type of atom, which there are possibility either can be here or here. So, let us say this is a B2 type of structure first. B2 means let us say a ordered type of structure, and inside that it is a BCC based structure. So, you can get a one type of atoms here, and this is the second type of atom, a very general case like how this ordering takes place and so on. So, this is another one type of atom, where the possibility of getting this atom can be also here. Okay. And this is a typical direction of 100 of B19, and this is 010 of B19 martensite. So, for parent phase we can think about basically 3 different possible correspondence lattice. How? Let us say a type of lattice, where this is the structure of the lattice, this atom should move here, and this will move here, and this will move here. The second is the B type. So, one is the A type, another one is the B type, and the third one is the C type. Here you see this is again the same structure, and we can get this from the in the martensite B19 structure. Now, the transformation that is required from B2 to B19, that is a parent phase to a martensite phase, is that is a desired phase. However, the 3 different correspondence that occur by the reverse transformation from B19 to B2, because once it is a ordered structure, we have to go back from a B19 to a B2 structure. Now, how is the B2 structure, that is the parent B2 structure? If we take a type of B19 structure and transform into a B2, then it will looks like this. So, here are the atoms, and this is another one, this is the alternative position of this atom, and this is another 4 atoms. Okay. So, this is the ordered structure, and it is the half 010 direction of B2. Okay. So, we basically get back the initial ordered structure to the parent structure. So, how it is, again you can have a look here. So, if I join this lattice, okay. So, I simply move it here, I simply move it here, I simply move it here, I move it here. So, it is a type of lattice, and I get back the original B2 structure from a type of lattice. Okay. And now, interestingly, if I choose a other different correspondence like B and C, then from here you could easily see that I will develop such a structure, okay, where the original structure it seems will not be back, okay, because here this should be in the alternative directions, right, and here should be the black one and here should be the opposite one. Okay. So, there will be a problem to get back the original parent structure and the transformation strain will never be back. So, it is very much important that which way the system choose to transform from a product phase, that is martensite, to its parent phase, which basically linked to it the parent phase differ from the B2 structure, because this is not the original parent structure which is desired, which we have started with. So, this is just a wrong sequence actually. So, from the path B and C, if we choose any of these lattice correspondence and try to go back to the parent structure which is a B2, instead of going that it basically goes here, and so the free energy of the parent phase basically rises and the transformation is not possible. So, the reverse transformation from B2 to B19, this reverse transformation and their lattice correspondence is very much important, because there is a ordered structure, and if we have to again get back that ordered structured parent phase, then a proper lattice correspondence has to be chosen. That is why this is not only a case for nickel titanium, for many other system also, wherever there is a B2 to B19 type of structural transformation actually occur. Now, let us have a look at what are the various systems so far we have discussed. So, in case of a copper nickel and copper zinc system, we have added aluminum, and these are some of the properties of these systems. Please have a look in case of a melting temperature, density and so on. So, something very much interesting to notice here, like copper zinc, copper aluminum, beryllium system, the melting temperatures are relatively lower than the nickel titanium. So, here nickel titanium is preferred for in such a case, whereas if you simply look at the biocompatibility, the nickel titanium is the best for as a biocompatible elements, because it contain, and the beryllium containing alloy is not preferred at all. However, if we look about the one way or a two way shape memory effect, then the maximum strain can be generated in a nickel titanium system, which is around 8%. This is a huge strain actually. So, we can get back that strain, whereas the transformation domain is very well in case of a copper aluminum beryllium system, where we can go from -200 to almost 150. So, we can tune the transformation temperature a large, and so this is for a very industrial application we can have a very useful. If we look about the tensile strength, they are somewhat in the range of 800 to 1000 megapascal. So, which is quite good, and also we may have a relatively low Young's modulus that can be achieved in this case, where the total transformational enthalpy is very high in case of nickel titanium. The expansion coefficient is also very less in case of nickel titanium, and so there is a large biomedical application. By looking at these properties of nickel titanium, we can simply suggest. So, that is very good in case of such a system, whereas in case of a high temperature behavior, the copper aluminum beryllium system could be exploited more. Now, in case of this nickel titanium system, there are so many different alloy composition I have shown here. These are somewhat a nickel rich alloy. So, you can see the nickel 50 or 0.5 or 51. So, in this particular case the MF or MS temperature could be tuned from a 50 to minus 114. So, 114 degree centigrade. So, that is why we said that the transformation domain could be minus 100 to plus 100. So, this is quite good, but not so good compared to copper aluminum beryllium system. Whereas, if you replace nickel with the help of some amount of copper, then we can think about getting a much lower MS and niobium, hafnium, zirconium, palladium or platinum. These are some of the elements that can replace some of these composition, and so that we can tune the martensitic transformation temperatures quite wide. So, let us say in case of titanium palladium system we can reach up to 550 degree, whereas we can also go up to minus 175 degree, 175 degree. So, you can see there is a large possibilities of all these different shape memory alloys and their application oriented material development that goes on during this period. And if we critically look at some of these titanium nickel system, then you will see that here I show here with the x is the atomic percentage of ternary alloy addition in nickel titanium system with the change of MS temperature, that is represented with delta MS. So, the I am just talking about the change. So, if we first take an example like gold or let us say the palladium and so on. So, usually the hafnium concentration if we increases, then MS temperature goes in the positive side, where chromium for nickel or manganese for nickel, they change the transformation temperature quite a lot, like cobalt, or let us say in case of palladium and so on, we can change the MS to a negative side to a large extent. So, so far we have discussed the most important systems or non-ferrous systems in non-ferrous shape memory alloy, and we have learned that various transformational product that may encounter during these austenite to martensitic transformation, and the situation could be very complex in case of nickel titanium. So, the purity of the alloy is also important. Why we are discussing about that? Because sometimes we may producing some alloy from a not a very let us say the highly pure elemental composition, let us say 1% or 0.1% aluminum is there in a nickel titanium alloy, which will change all the transformation temperature. So, the purity of these advanced alloys or shape memory alloys are very much important, so that for a particular type of application we know the selected MS and MF temperatures. And with this we complete today's discussion on the non-ferrous shape memory alloy, and we will continue some other case studies and particular mechanical properties and the application oriented discussion in the next classes. Thank you.